Hello, my name is David Velazzi, and I'm an exploration geoscientist with NEOS Geosolutions, and today I'll be presenting to you the Neuquén Basin case study. I will begin with an introduction and a look at the NEOS integrative approach in the Neuquén Basin, and then we'll take a look at the regional and geological context. Then we'll look at the magnetic and gravity data and see how we integrated it with the existing seismic and well data to delineate the basin architecture and the volcanic placement. And we'll look at the dominant structural trends and see how we integrated it with our acquired hyperspectral surface data. Then we'll get into the 2D and 3D modeling. Then we'll look at our high-graded areas, both our qualitative and our quantitative high-graded areas through predictive analytics. And we'll wrap it all up with a final conclusion map. In 2011, a supermajor approached NEOS and was interested in high-grading acreage in the emerging Vaca Muerta shale play. Now, they had a lot of seismic in the area. However, the quality of the seismic wasn't very good due to the large amount of surface volcanics in the basin. They're also interested in the frontier areas of the basin, which had a limited amount of well data. These frontier areas also had all the pertinent petroleum source rocks and reservoir rocks that outcrop at the surface, and also had the most modern tectonic regime fabric imprinted on these rocks. It was all these factors that made this a great basin and well suited for the NEOS technology and our integrative approach. If we look at the NEOS exploration approach in the Neuquén Basin, we took existing seismic and well data and interpreted it and mapped it up. Then we went out and acquired magnetic data, gravity data, hyperspectral data, and did a fair amount of groundwork in the basin. This groundwork involved both geochemical sampling for the pertinent source rocks, for TOC and thermal maturity, as well as hyperspectral ground truthing. Hyperspectral ground truthing was basically collecting spectral measurements of all the pertinent outcrops, vegetation, and hydrocarbon seeps in the basin. We then individually interpreted all these different data sets and integrated them to get a basement to surface insight. This presentation will essentially highlight some of the key highlights from this workflow. We look at the regional context of the Neuquén Basin. We're going to go on a little Google Earth tour. The Neuquén Basin sits in the country of Argentina in northern Patagonia. Here it is outlined in black. The Neuquén Basin is approximately 44,000 square kilometers. It's bordered on the east by the Las Pampas and the north by the province of Mendoza, which is famous for its Malbec grapes. And in the southeast portion of the basin sits the city of Neuquén at the confluence of two rivers, the Rio Neuquén and the Rio Lamay. The western boundary of the Neuquén Basin sits the Andean Cordillera, and outlined here in yellow is the country border between Argentina and Chile. If we look at the conventional oil and gas production in relation to the major structural elements in the basin, what we see is most of the conventional oil production is up on the flanks of the basin, both up here in the northeast platform and down in the southwest on the flank called the Huinco Uplift. We also get a fair amount of oil and condensate in what's known as the Neuquén embayment outlined here. Most of the conventional gas production is restricted to the structural and topographic high called the Chorritos High, which essentially sits in the center of the basin. And as we get west into the basin, we get into the more frontier areas of the basin in what's known as the aggregal fold and thrust belt. And this is the modern-day compressional regime. And as we get further west in the basin, we get up into the Patagonian Cordillera. If we look at the surface geology in the Neuquén Basin and kind of highlight some of the key features geologically in the basin, starting from east to west, we get a large amount of surface volcanics. Outlined here in the northeast by this purple is this big stratovolcano called the Agua Mojito. This is an extensional related feature of Pliocene in age. To the west of that, we get, again, this big basaltic complex here outlined in purple. This is the Sierra de Juan Treca. This is a compressional Miocene age platform. In the center of the basin, outlined by the green and yellow colors, these are our late Cretaceous sands and tertiary fields. And as we head west into the basin, into the frontier portion of the basin, is where we get into our interesting geological outcrops. These are our major petroleum source and reservoir rocks. Outlined here by the lime green colors are the Agrio Shale, and in the light blue is the Vaca Muerta. And as we head further west, we get into the Andean volcanics, outlined again by these purples and reds. Up here in the northwest portion of the Neuquén Basin is this big Precambrian basement complex called the Cordillera del Viento. Again, this is a basement complex that essentially outcrops at the surface. NEOS conducted a multi-phase program in the Neuquén Basin. Phase 1, 2, and 3 combined for more than 12,000 square miles. Phase 1 was acquired in 2011, which sits here outlined in black in the Agrio Fold and Thrust Belt. Phase 2 was acquired in 2012, both in the Fold Belt and the Cordillera, and we have recently completed the Phase 3 portion, which sits more in the foreland center portion of the basin. All three of these phases we acquired magnetic data, gravity data, and hyperspectral data. We are also in the planning stages for a Phase 4 and a Phase 5. This will essentially complete the provincial portion of the basin. We're now going to go on a hyperspectral flyover. The flight path is outlined here by this red line. We'll essentially start up in the oil fields, cut across the basin, and then head north and land up in the Cordillera del Viento. This is essentially going to show you the quality of the data and highlight some of the major features that I've previously discussed. We're starting our flight path over the oil fields. These are all the Vaca Muerta sourced. And as we bank here, we're flying over this basaltic complex. This is the Sierra de Juan Trico. NEOS modeled this as having a thickness of over 1,000 meters. And as we cut across the Sierra de Juan Trico, we are starting to get in the Agrio Fold and Thrust Belt. Here you see we're crossing the Rio Neuquén, and now you're starting to see and get a sight of the resolution of some of these structures in the Fold Belt. Again, this is where all the predominant petroleum source rocks and reservoir rocks actually outcrop. Now, we use this hyperspectral data for a variety of interpretation products. We are able to get direct and indirect hydrocarbon seepage, indirect meaning alteration minerals, including clays, irons, and carbonates. We also use this to get a high-resolution geology map as well as a lithology map. Now, as we head north here, we're again going to cross over the Neuquén River, and you can see all the red coloring. That's essentially vegetation which forms on the banks of these rivers and along the slopes. And we will land again in the Cordillera del Viento. This is this basement outcrop complex that we see up here in the northern portion of the basin. If we look at a stratigraphic column in the Neuquén Basin, we have this pre-Triassic economic basement outlined here by this red block called the Choya Group. We had three major flooding episodes in the Neuquén Basin which deposited our three major source rocks in the basin. The Los Mojes, outlined here by this blue box, the Vaca Muerta, and the Agrio. The conventional reservoir rocks in the Neuquén Basin are a combination of carbonates and sandstone reservoirs. We get the Quintuco Reservoir, which sits above the Vaca Muerta, as well as the Molichinco and the Troncoso. These are fluvial and aeolian sands. We take a closer look at the Vaca Muerta and the Quintuco system. What we see is the Vaca Muerta has productive intervals throughout its entire Tethonian section. We have cyclical carbonates in the top portion of the Vaca Muerta, and as we get deeper in section, we're getting more into the marls, and as we get into deeper portions of the Vaca Muerta, we're getting into our more organic charged shales. These are our anoxic black shales. If we look at the Vaca Muerta and the Quintuco and see how it's defined by seismic, we can see that it's this carbonate ramp setting where we go in the east to the west. East is the more proximal, and as we get in the western portion and the more distal portions, we're getting into deeper water and we're getting a thicker Vaca Muerta. At the top of the Vaca Muerta, outlined here by this green box, is this prograde incliniform, and that's how it's interpreted in the seismic section. I'll point your attention now to the image down below here, this pie chart. This is a chart showing how the Vaca Muerta stacks up to some of the other major unconventional shale plays, such as the Eagle Ford and Bakken. As I mentioned, we have productive intervals throughout the Vaca Muerta, the TOC ranges from 4% all the way up to 8% into that deeper basal organic shale section. In comparison with, say, the Eagle Ford and the Bakken, we have a high amount of quartz and lower amounts of clays and carbonates. And this is, of course, important in terms of frackability. And as you can see, the Vaca Muerta has very good reservoir characteristics. When we look at the NEOS acquired gravity map and compare it with the surface geology, and we do a first pass interpretation, we are able to outline these areas here in white that are gravity lows and interpreted as subbasins. These are interpreted as having a thicker sedimentary package, as opposed to the gravity highs, which are the warmer colors, which are interpreted as gravity thins, which have a more basement influence, which have a higher density. So when we take a look at this gravity and compare it to the surface, we're starting to get a first pass idea of places that we might want to start looking at. And these are insights that are revealed that we don't necessarily see within the surface geology. So when we take that first pass interpretation a little further, and we look at the IHS Eden public well data, this is a map of the Vaca Muerta isopack. And as you can see, the warmer colors are the thinner Vaca Muerta up here on the flanks in both the northeast and the southwest. And as we get more distal, more west into the basin, we're getting a thicker Vaca Muerta. And when we look at that over a regional seismic line, outlined here in the bottom by this black line, and a regional stratigraphic cross-section outlined here in this blue, with our gravity data, what we see, this gravity high here is interpreted as being the Tritos high. And what we have here is a thinning of the Vaca Muerta, both in the stratigraphic section, Vaca Muerta here being blue and the light blue being the Quintuco. And in the Vaca Muerta in the seismic section, also we see a thinning over this Tritos high. Here the horizon in blue is the Vaca Muerta, where we're getting a thinning up on that structure, and off on the flanks we're getting a thickening. So when we look at that, and we look at that to our gravity subbasins that we mapped out here in white, we also have TOC from the Vaca Muerta. These are average TOC from chord intervals, and what we see is very interesting. We're getting lower TOCs up on top of the structure and higher TOCs on the flanks of these mapped subbasins. So this is further evidence that these gravity subbasins are places that we want to start looking and start diving in and doing more exploration. We look at the NEOS acquired magnetic data, and we have both deep and shallow magnetic sources within our data. It's important that we want to separate these out so we can interpret what is deep magnetic signal and what is shallow magnetic signal. This is important for a variety of reasons, from both a thermal maturation to also a geohazard. And our clients are very interested to know where these intrusives and where these deep magnetic bodies and shallow volcanic source bodies exist. This is, on the left is the deep magnetic data from our phase 1 and our phase 2 study area, and our shallow magnetic data on the right. And what we see outlined here in these warmer colors is our interpretation of a deep Paleogene magmatic arc. We also have another deep volcanic stock here outlined by these warm colors. When we look at the shallow magnetic data, we see it ties up very well with what's known in the surface geology, where we have these Paleogene surface volcanics and also these younger Miocene surface volcanics. If we look at the magnetic data in the phase 3 portion, the foreland portion of the Neuquén Basin, we're really starting to get some interesting features pop up in the deep. Here outlined by these warmer colors that are interpreted as deep volcanic stocks or subbasement plutons. And again, also in the shallow, it's doing a very good job of what is known within the surface volcanics here in the Sierra de Juan Trico, the Aqua Mojita, and the Parva Negra basalt. And what's interesting is you can start seeing some connectivity between the deep volcanic stocks and the shallow volcanics that exist at the surface. And so you can start really looking at it from a thermal maturation standpoint and the geohazard standpoint. We look at the dominant structural trends that were mapped. We did an integrated approach where we took all the magnetic data, the gravity data, the seismic data, and the well data, as well as surface geological maps and published data sets, and we were able to come up with an integrated structural fault interpretation. The fault interpretation here is in black, and it's overlaid on the gravity tilt on the left and the hyperspectral on the right. And what you see is this dominant northwest structural trend. This again is associated with the modern day compression where the Nazca plate is subducting under the South American plate. And as a result, we're getting these large north to south high angle reverse faults. We're also getting two other trends that we see in the data. These are essentially wrench faults coming off the major dominant trend. We get a northwest to southeast and a northeast to southwest. NEOS did a fair amount of groundwork in this basin. This included both hyperspectral ground truthing. Again, as I mentioned earlier, this is used for hyperspectral processing and to aid our interpretation, where we're collecting spectral signatures of all the pertinent geological outcrops, vegetation, and known seepage. And we use this for both our processing and to aid in our interpretation. We also did a fair amount of geochemical work in the basin. This was to get TOC in thermal maturity values for both the Vaca Muerta, the Agrio, and the Las Morges. We also collected susceptibility measurements of the surface volcanics as well as the basement outcrops. And we also collected gravity measurements that were helped to calibrate with our log values. And these, of course, went into our inputs into our 2D and our 3D modeling. If we look at the hyperspectral surface products, what we see here in this map are our direct and our indirect hydrocarbon seepage. The direct are the lime green circles, and the indirect are the pink and the dark green. And what we see, as you would expect, we had most of the seepage is off the volcanic cover here outlined in black, and it's both in the aggreofold and thrust belt portion as well as in the foreland portion of the Neuquén Basin. If we take a closer look at that, and we look at the fold and thrust belt, what we found was the direct and indirect hydrocarbon seepage were not actually found along map faults, but we found these along the known surface fold structures within the aggreofold and thrust belt. We found these both in the cores of these anticlines as well as in the synclines. And as well as that, we found a lot of these on the flanks of these anticlines, both in the context of the Agrier and the Avile and the upper Agrier and the Huturan. This is just another look with our hyperspectral acquired data of where some of these seeps occur. As you can see here, we have some seepage here found in the toe of the anticline and down here in the core of this anticline. This is important for a variety of reasons, and our clients were very interested in our findings from our direct and our indirect hydrocarbon seepage. And they actually sent out geologists out to the field so they could type these seeps back to their source. We look at the foreland portion of the study area, the phase 3, we find a different scenario. Instead of finding our direct seepage along folds, we actually found them along some of our major map faults. In particular, there's one fault called the Cordilleras Liniment, outlined here in black. Here you can see that we get a lot of direct hydrocarbon seepage along this mapped fault, the Cordilleras Liniment, and then down here as well where you can extend it, and we're seeing again a lot of direct hydrocarbon seepage. Here I propose that some of these transpressional wrench faults actually have an extensional component to them, and this major fault possibly has an extensional component where a lot of this seepage actually had a migration pathway to find its way up to the surface. As I mentioned, we did a fair amount of geochemical work on outcrops, and we also collected spectral measurements on these outcrops. So we were able to map TOC from spectral measurements, train the data, and get an airborne TOC map. And this is that map. We have high TOC in red, yellow in moderate TOC, and in blue the low TOC. The most important finding here was the high TOC, the red colors, had a very good correlation with that deep basal portion of the Vaca Muerta that I mentioned earlier has the higher TOC and the higher organic section. And we found that from our aerial mapping that our highest TOC was also within this section. So 2D modeling, once we put all this stuff together as far as all the groundwork we did and all the well mapping and the seismic interpretation, we're able to map up some of the key horizons, such as the basement, outlined here by the pink, and some of our key target horizons, such as the Vaca Muerta, as well as the surface volcanics. We do a large amount of strike and dip 2D sections, and what we do after we forward and inverse model, we export out these horizons, and we regrid to get a 3D surface, and then we redo the modeling in 3D space, and again, forward and inversion. This is the result of the 3D model. This is the top of the economic basement. On the left is the 3D view, and on the right is the 2D planar view. The warmer colors are the higher structural relief, and the cooler colors are lower. And what we found was the sedimentary basin as deep as approximately 8 kilometers off the Triato High to the west, outlined here, which is known as the Huacalera Trough, and also in some of these deeper pockets over in the Agrio Fold and Thrust Belt, as well as some deeper pockets that exist below some of the thick volcanics that I mentioned, such as the Sierra de Juan Trico. We also had a basement as shallow as approximately 1 kilometer, and this exists over in the western portion of the Phase 2 area, where we're getting this long north to south structural trend where we're having basement essentially almost outcrop up into the surface. If we look at the top of the Vaca Muerta after the inversion, we see it as a pretty similar trend to the basement, where we get this big structural high, interpreted as a Triato High, getting another high up here up in the Neuquén platform, and off these structures we're getting down in the deeper portions of the Vaca Muerta. But as we head west, what we see are we're getting these big structural highs of the Vaca Muerta, and this is a result of our reverse faults that are splaying off the basement and causing these repeat sections of the Vaca Muerta, and that's why we're getting some of these structural highs here. And as we head west, the Vaca Muerta essentially either outcrops at the surface or is getting eroded out. If we look at the Vaca Muerta isopack and we drape it on the basement structure, that's what we have here in 3D view on the left and in 2D planar view on the right. What we see is very interesting. In the structural highs of the basement, here in the Triato High and up here in the Neuquén platform, we're getting the Vaca Muerta thinning, and as we get off the structure into these pockets, that's where we're getting the thicker Vaca Muerta. And in our thicker sections, again, we're getting these repeat sections of the Vaca Muerta where we're getting very thick. And as we head further west, again, we're getting very thin Vaca Muerta because it's essentially either outcropping or eroded out. If we go back to our first pass gravity interpretation and overlay it on the result of our Vaca Muerta 3D model, we see that there's a very good correlation between our first pass interpretation and what we now have as the output from the model. Again, we have the whites of the gravity subbasins and the warmer colors of the Vaca Muerta thicks, and we see a very thick Vaca Muerta correlating well with our gravity subbasins. So once we have the GRV from the Vaca Muerta model isopack, and we take a look at the porosity and other well log analysis, as well as regional public known values, we're able to calculate the gas in place and oil in place per square mile for the Vaca Muerta. On the left is the Vaca Muerta gas in place map, and on the right is the Vaca Muerta oil in place map. What we found for gas in place is an average of 318 BCF per square mile. And for oil, what we found was approximately 47 million barrels per square mile. We did a whole uncertainty study on this base case, oil in place and gas in place. But as a geologist, the most pertinent maps that I like to look at are probability cutoff maps. On the left is the oil in place probability cutoff map for greater than 20 million barrels per square mile. And on the right is the oil in place cutoff map for greater than 100 million barrels per square mile. So if I'm a conservative, not really a risk taker, I'll look at the oil in place for greater than 20 million barrels per square mile, outlined here by these warmer colors, and these are areas that I might want to start looking further. But if I'm more of a higher risk, higher reward, I like to look at the greater than 100 million barrels per square mile, and these are some of the areas up here in the northeast portion that I'll want to start looking at. So after we do all this, we put it all together, and we want to start qualitatively high-grading acreage. Some of the things we started to look at were both our gravity subbasins that we mapped, our sub-basement plutons, the proximity to these magnetic highs, our fault interpretation, we looked at the gas to oil ratio, we mapped that out to look at the areas that were more oil prone, and we looked at our oil in place and our gas in place maps, as well as taking into account the Vaca Muerta isopack and the Vaca Muerta structure in the basement effects. So what we have here are high-graded exploration areas. We did this both for oil, wet gas, and dry gas. The white boxes are the areas that we high-graded for oil. The blue boxes are the areas that we high-graded for wet gas. And the black boxes are the areas that we high-graded for dry gas. Now, since we didn't have any production from the Vaca Muerta in this area, we used these qualitative high-graded areas to pick training points to train for our correlative predictive analytics. And that's what these black circles are here. We took 3 training points within each box to run our predictive analytics. Now, this is the result of the predictive analytics. We ran this both for oil, wet gas, and dry gas. I'd like to point your attention to the oil predictive analytic map. The warmer colors here represent a higher similarity to the training, higher geostatistical similarity to the training points, and we use this to high-grade acreage. We were able to create an oil AOI based on a 70 similarity contour, and what we found is we got an oil AOI of approximately 1,500 square kilometers, and this is essentially 15% of the entire Phase 3 block. We also did the same thing for wet gas and for dry grass. So in conclusion, shortly after NEOS finished this study, Exxon announced the successful Bajo del Choique well. This is the most successful Vaca Muerta well to date in the Neuquén Basin, which had an IP rate of approximately 770 barrels of oil per day. And as you can see, the Bajo del Choique well here sits both within our qualitative high-graded area, the white box, as well as our predictive analytical high-graded AOI area. I think this is a good confirmation of the work that NEOS has done in the integrative approach. It shows we did a relatively quick, non-invasive way to high-grade acreage and help our clients make better decisions on where to drill and just as important, where not to drill. Thank you very much.